Recording, and I'm starting screen demonstration. Now it is full screen, and today's topic. Today we will discuss two topics. It is magnetic field and electromagnetic radiation, electromagnetic wave. Last lecture 2 weeks ago we were discussing electric field, and we have discussed its application for cardio diagnostics, which is known ECG, electrocardiography. And today we will discuss some things related to magnetic field. We will begin with the fundamental concepts, and then we'll consider one application of this very interesting part of physics. The application is magnetic resonance imaging, or in Russian more often you can hear magnetic resonance tomography. So again, we'll start with basic concepts. What is magnetic field? The magnetic field is, according to modern concept, it is a part of electromagnetic field. It is its manifestation which which produces the force acting on moving objects. If we compare it to acting on any charged particle independently of its velocity, independently of is it moving or not, the magnetic field acts only on those particles which are moving in space. And the force, which is called Lorentz force, the force related to magnetic field, is given by equation 1, where you can see this force equal to Q VB sine alpha. So Q is charge of particle, V is its velocity, B is magnetic field, and alpha is angle between vector V and vector B. So the maximum value of force will be when the angle alpha is equal 90 degrees. So we can say that B and V should be perpendicular to each other. And the force FL, it also has some direction. So this direction is to be perpendicular to both V and B. So this is modern definition of vector B. In modern science, magnetic field manifests itself through this vector B, and this B defines the force acting on a moving particle. Of course, it was not understood early times in the beginning of study of magnetic field. People are people know the magnetic fields from very old times, because magnetic interaction of permanent magnet was seen by antique people, and this type of interaction was not understood until 19th century. It could be considered as a completely different interaction, different with electric field. But in 19th century, it was shown that the magnetic fields can interact with electric currents, and electric currents interact with each other by magnetic interaction. So, well, I'm trying to mute someone's microphone. I don't know. Well, in 19th century, magnetic interactions was first found as an interaction between electric currents. And this can be considered as a consequence of equation 1. So if we have um, a particle moving with velocity v, charged particle, then magnetic field will act with a force on this particle, and the force acting on many particles will produce the force acting on the wire with current. And so this is known as ampere force, or force of interaction of magnetic field and electric current. So, of course, it was seen before the Lorentz formula was found, because people deal with electric current before they started studying charged particles. That's why it was easy to investigate currents than to investigate moving particles in vacuum. Well, and according to this formula, we can see that if the wire has a current in it, then there is a force acting from magnetic field to the wire, and this force is given by equation 2. And let us make a step back. So here we can see two type of quantities that can characterize magnetic field. It is B and H. What is the difference? The difference is that B represents the force which appears in magnetic field, and H is used when we are finding a magnetic field produced by some currents or other sources of field. And there are magnetic materials. The magnetic field can be produced by moving electrically charged particles, and it can be produced by intrinsic magnetic moment of some particles. And there are some materials where this intrinsic magnetic moment makes a big contribution into the total magnetic field. Those materials are called ferromagnetics. And in case of presence of these materials, it is not easy to get immediately the magnetic field produced by current. We need to know the magnetization of magnetic materials. And to simplify the way of finding magnetic field, the second vector characterizing each was introduced. It is vector H. The basic property of this vector is that each includes only contribution from currents. When we are finding magnetic field, and we start with finding field H, we should not take into account material magnetization. We take into account only electric currents. And then when we are looking for B, we should add both contribution from electric fields, from electric currents and from magnetization. So this second vector is suitable in solving problem of finding a magnetic field. And action of magnetic field is characterized by vector B. Now let us go further. So this is the right-hand rule, which allows one to find the direction of force acting on current. It is interesting that when I was in school, we have studied not right-hand rule, but left-hand rule. In Russian textbook, you can find a left-hand rule, and it looks similar, but the direction of vectors associated with the palm is completely different. In left-hand rule, the palm is taken, fingers are directed along the current, and B is coming into the palm. Then the direction of thumb gives us the direction of force. Anyway, since I have found in English Wikipedia this right-hand rule, it is very likely that it is more widespread in English-speaking world. So let's just use it. The right-hand rule, and the picture explains how to use it for finding direction of F. Actually, I will not give you problems for these directions. You just need to know that F is perpendicular to both I and B. Well, and as I told before, the magnetic field in 19th century was introduced as a field describing interaction of currents. So initially, the laws of interaction were established without any field. So there were laws of interaction between one wire with current and another wire with current. But later it was understood that it is the problem becomes simpler if we divide it by two parts. In first part, we find magnetic fields produced by the first current, and the second part, we find the force acting from magnetic field onto the second current. So in this case, it is necessary to be able to find the field produced by infinite straight wire, and this problem can be solved directly, and it shows that the magnetic field is directed tangential to, well, I have someone I see that someone have raised a hand. What happened? Do you need something? Gubran Sarhan. Do you hear me?
Yes, sir.
Yes.
Okay.
Yes.
So
Yes, sir, we can.
I see it is because so we will continue. So I will not mention and so the magnetic field of straight wire is directed tangential to the circles with the center on the axis of the wire and the plane perpendicular to the wire. So it is shown on this picture. And the absolute value of magnetic field is given by equation 3. This is valid for infinite straight thin wire. If we compare this equation with equation of electric field of point charge, for example, we can see that here we have r to power 1 in denominator, and in case of point charge, we had r to power 2 there. So one can assume that the law of decrease for magnetic field is different from the law of decrease of electric field. But it is not right. The law is the same. The difference is because of different geometry of the source. If we discuss a point particle, it is a point, and infinite length thin wire is a one-dimensional object. Point is zero-dimensional object, and wire is long, and it has another geometry, and that's why we have r to power minus 1 in this formula. If we consider it an electric field produced by infinite length thin wire, for example, charged wire, then we would have the same law of decrease for electric field. So it means that if we were having a point source of magnetic field, its field would probably decrease as r to power minus 2. But point source in case of magnetic field is not easy to find because basic sources are currents, and currents are going through the wires with some length. They can not be a point object. And we can consider something like point object if we divide the wire by infinitely small parts, and each part produces its own magnetic field. In this case, the field produced by small part of the wire uh, decreases as r to power minus 2. But when we sum the field produced by all of them, all these small parts, we obtain equation 3. And one important thing concerning magnetic field is an electric field. The magnetic field also satisfies the principle of superposition. It means that magnetic field produced by several sources equals to a vector sum of fields produced by each of them. So the magnetic fields of different sources does not uh, interact with each other. They just sum as vectors without any change. Or one field does not change the field produced by another sources. This is a very important superposition principle, and according to modern science, it is valid for electromagnetic fields for both electric component and magnetic component. Superposition principle is valid. Well, and from the equation for magnetic field produced by a straight wire, we can get an equation for force of interaction between two wires. Actually, experimental study starts with this equation. So, as I told before, initially we had the experiment on interaction between two wires, and then to understand this experiment, we introduced this force, and after that, this force was um, decomposed into two two factors. So first is field, and the second is force acting on second current. So field produced by first current acting on the second current. And you can see the first term here, mu0 2 divided by 2 pi r I1 can be considered as a magnetic field produced by current I1. Then it interacts with current I2. And the force of interaction is proportional to the length of the wire. So each small part of wire feels the force given by equation 4. And this equation is known as Ampere's force law. Again, we can see that the force of interaction between two wires decreases as r to power minus 1. That is because of the geometry of wires. Wires are infinitely length one-dimensional objects. Well, and the direction of interaction in this case can be found g there. Then in general case, if we have two parallel wires, then they are attracted one by another if they have the same direction of currents. So parallel currents are attracted, and anti-parallel currents are repelled. So they repel each other. And we don't need, for this rule, we don't need to use, for example, right-hand rule every time. But of course, if we do so, if we use right-hand rule, we will get the same result. So F2 will be directed towards current I1. Well, and next thing concerning to magnetic field is that we have interaction with magnetic field every time. We don't feel it. Our body does not have a good sensor to be able to feel even strong magnetic fields. And anyway, there is an important property of our world. It is presence of magnetic field of Earth. So Earth's magnetic field is very important for life on our planet because it protects us from charged particles which goes from sun with very high energy. If there were no magnetic field, those particles would reach the surface of Earth, producing strong ionizing in every objects, including living objects too, including human, animals, and plants. So ionized radiation is very dangerous in high dose, and if we had no magnetic fields, then the doses will be high enough to kill many animals. So this is very good for us that we have this magnetic field protection. And how it works, if charged particles uh, comes inside the area with magnetic field, it becomes rotating around the vector of magnetic field. So if each has a component of velocity parallel to the magnetic field, this component will be conserved, and it means that the particle will have spiral trajectory. In uniform magnetic field, the moving particle moves along the spiral trajectory, uh, and its rotation in the plane perpendicular to um, the vector of magnetic field prevents its motion in the direction of this plane. So it cannot move far away in the direction perpendicular to magnetic field. And it can move parallel to magnetic field. So if we discuss non-uniform magnetic fields, then the particle will move along the lines of magnetic field, and it will move around the spiral trajectory around the vector of B. So in case of Earth's magnetic field, the particles will move to the poles, and that prevents most of surface of the Earth from very strong flow of this hardly um, this highly energetical particles. And what is interesting with magnetic fields that this type of motion does not depend on particle energy. Even with very high energy, it will move parallel to the lines of magnetic field. It is because the higher energy is, the higher speed of the particle, but on the other hand, the higher uh, force acting on this. So the higher speed, the higher force. That's why the effect is similar to highly energetical particle and low energetical particle. This is very good protection. If we compare it to electric fields, for example, if we try to protect the planet from particles by electric fields, then the uh, higher energy of particles, the higher electric field is to be used for this protection. And that's why we would be unable to prevent uh, penetration of very uh, highly energetical particles in this case. But in case of magnetic field, even quite a weak magnetic field is enough to prevent this uh, penetration. And what the field of magnetic field look like in space? What is the shape? The shape of this field is similar to the shape of a field of so-called point magnetic dipole. We have studied an electric dipole, which consists of two point charges with different sign and the same absolute value. In case of magnetic field, the elementary point magnetic dipole can be considered as a small current loop. So here we can discuss it. Please mute your microphone. Well, please check your microphone and turn it off. I don't know who is speaking now, who produces noise. Well, Signal John didn't found is making noise. Well, I'll try to continue, but once again, if you are listening to me, if you hear me, turn off your microphones because there are too many people here.
Please turn off your microphone, everyone.
So, as the host, you can mute everybody's mics.
And how can I do this?
Yes, teacher.
So,
Can
you
you
will
go
have
to
an option
participant?
on your screen to mute all participants.
Wait a second. Mute your I didn't use it before, so I don't know where it is.
So, if you go to the participants list, you can see an option to mute all participants.
Oh, okay. Well, let me see. Yes. Okay. I have mutual participants now. So if you need to ask me something, please raise your hand because I will not react on your messages in chat because in chat you are writing your names for your attendance. So let us continue and we will discuss the point magnetic dipole, which is actually important from 2 points of view. First one is that a magnetic field of Earth looks like a field of a point dipole, but there is another important implication of this is that a magnetic field produced by small elementary particles is it has the shape of magnetic field of point magnetic dipole. And what can we call this point magnetic dipole? If we consider a circular loop and we'll study a magnetic field on distances which is much larger than radius of the loop, then we can find that this magnetic field depends mostly on a quantity which is called magnetic moment Pm, which is equal to product of current I and area of the loop A. So at large distances, the shape of the loop, the maybe what else? The width of the wire with current. So this becomes not important from the large distances. We cannot distinguish different shapes. We cannot understand if the wire is thick or thin. The only quantity which describes magnetic field of small current loop is its magnetic moment. And if we consider a rotating charged object, so then it can be considered as a set of currents. So a part of this rotation object can be considered as a closed loop, and the current can be found, it will be proportional to the speed of rotation and to the total current of the total charge of the object, and it will be proportional to the um, the current will be defined by these two um, quantities, I mean speed of rotation and total charge. But the magnetic moment will depend also on distribution of charge inside the rotation object. And a rotated charged object creates a magnetic field which looks similar to magnetic field of a point magnetic dipole. And you know that all the matter consists of different various elementary particles. In the simplest model, we can take into account only three types of particles. It is electrons, protons, and neutrons. And the protons and neutrons are part of atomic nuclei. So if we consider atoms, we can speak about electrons and nuclei. And electrons and nuclei of atoms are both charged. The nuclei is charged positively, and electrons are charged negatively. And the total charge of atom equals 0. But both particles, electrons and nucleus, they both have their own magnetic moment Pm. According to modern theory, the movement of such small particles as electrons and atomic nucleus is to be described with the laws of quantum mechanics. And from the point of view of quantum mechanics, we cannot say about rotation of small particles around their own axis. We cannot consider them as rotational objects like our planet is. But anyway, in quantum mechanics, it is states that the particles like electrons have their own magnetic moment, intrinsic magnetic moment, which is not related to space motion of the particle. And this magnetic moment can be considered as a point magnetic moment, a point magnetic dipole, and the field created by any elementary particle is similar to the field created by a point magnetic dipole. That's why it is very important to study this object, a point magnetic dipole. And the distribution of magnetic field for point magnetic dipole is the same as distribution of electric fields for point electric dipole. You see that the object itself looks different. In case of electric field, we had two charged particles. In case of magnetic dipole, we have a closed loop with a current. The objects is different, but the field produced by both particles, both objects in outer space, has the same space distribution. Let me look if I have this on my second slide. Well, I have it only here. If you compare it with previous lecture with field produced by electric dipole, you can see that lines of magnetic fields on this picture are similar to the lines of electric fields on those pictures. And next thing is the interaction of magnetic dipole with external magnetic field. So if we have a charged particle which is inside external magnetic field and which has a magnetic moment Pm, then we would find that the particle feels the choke M. So there is a choke that makes the magnetic moment to rotate around itself, and it tends to move the magnetic moment so that vector Pm will be parallel to the magnetic field B, external magnetic field. And if we have a loop with current in magnetic field, the choke will try to rotate it so that M will be parallel to B. In case of loop with current, if we don't apply another forces, then the loop will be orientated perpendicular to B, so that its magnetic moment will be parallel to B. But in case of charged particles, they have an angular moment associated with the space motion, and they have angular moment which is their intrinsic property. On a very raw model, we can consider it as a rotation of particle around itself. For example, our planet does. And I have told already that in quantum mechanics, it is shown that this model is not correct. But since we don't study quantum mechanics at all, we can use this model, remembering that it is not completely correct and it is not explaining every phenomena. But one important thing which can explain is the so-called precession motion. Precession is a motion similar to the motion of I have forgotten the English word for this. So if we discuss quick rotation objects, there is a toy for children which is made of something that can rotate with high speed, and this quick rotation object does not fall down. It moves so that its axis moves along some cone shape. It draw a cone shape in space. So this type of motion is called precession. And precession appears in case of a particle with moment Pm comes inside magnetic field B. That's why this particle does not orientate immediately parallel to magnetic field B. It starts precession instead of being orientated, instead of rotating in the direction parallel to B. It starts precession around the vector B. And this precession is important from the point of view of one medical application. let's just consider the next slide. It is magnetic resonance imaging. I would say that it is one of the most highly technological application, and if we discuss widespread physical highly technological techniques in medicine, this one is probably the uh, most technological, so it includes most complicated physical technology. Let me explain it first in my words. After that, I'd like to show you some video. We can see some video about MRI. What is MRI? First, it is a technique based on study of nuclear magnetic resonance. So we will discuss here the interaction of atomic nuclei with external magnetic field. And this is not only constant magnetic field. There are two fields used in this technique. One field is strong, and it is permanent field. It does not change in time. But another field is high frequency oscillating electromagnetic wave. And this wave interacts with precession atomic nucleus. And this interaction has the resonance nature. So it appears only if the frequency of precession coincides with the frequency of external field. That's why we can. And what is this interaction leads? This interaction leads to orientation of magnetic moments parallel to magnetic fields with the help of external high-frequency electromagnetic field. So the high-frequency field is absorbed by the object, and if it is a permanent high-frequency field, then the signal which can be detected is the signal of its absorption by the tissue. So if the resonance conditions are valid in some part of tissue, then the absorption of this tissue increases many times. And what is interesting is that resonance conditions depend not only on frequency, but they depend on external strong magnetic field. So we can change the frequency by changing of external magnetic field. And in experiment, the frequency is usually taken constant. So we do not change frequency. We change the external strong magnetic field. So the resonance conditions, and this field is not uniform. So the resonance conditions can be satisfied only in a small place of space, only in a small region of space. And the signal will go from this region only. And the signal will be proportional to the number of hydrogen nuclei of protons. Usually, for medical purposes, only one element is used, it is hydrogen. So the magnetic resonance appears on nucleus of hydrogen atoms. And that's why in the simplest form of this technique, we can get information about the distribution of hydrogen. So the higher concentration, the higher absorption will be in resonance area. That's why we can scan the human body and find the concentration of hydrogen atoms in different places. And this allows us to create some type of image. What is important, this technique is completely harmless. It is not dangerous. It does not produce any harm on human body in contrast to X-ray diagnostic, for example. And a more advanced technique allows us not to know only concentration of hydrogen atoms. It allows us to get information about its surrounding, so about the atoms which are which present surround the hydrogen. So it allows us to get information about type of tissue. If the hydrogen is in water solution, then some parameters of signal will be different from the hydrogen which is in fat tissue. So we can get distribution of water and fat using this more advanced technique. Well, let us see some video, then maybe I'll continue explanation of MRI, but first I'd like to show you some video. And this video can be found in a file. I will send you this file in our chat. I'm sorry, I'll probably need to stop my screen demonstration because at this moment you will not see you will not hear the sound, so I'll stop it. And I'll start it again in a few seconds. So this screen demonstration I need to use.
Welcome to Lightbox Radiology
Well,
Education.
tell me please, can you hear the sound in the video?
Yes, sir.
Yes, sir.
So let us continue. I get your response. So
MRI was discovered in 1947, simultaneously by two physicists, Felix Bloch and Edward Purcell. The first clinical images were obtained in 1977. MRI uses magnetic fields and radio frequencies, rather than ionizing radiation used in X-ray and CT. The magnetic field strength of an MRI machine is measured in Tesla. The majority of MRI systems in clinical practice are 1.5 or 3 Tesla, referred to as 1.5 or 3T. These produce an extremely strong magnetic field, up to 50,000 times that of the Earth's magnetic field. An electromagnet of similar strength would be able to pick up a car. The body is made up of 70% water, which is composed of hydrogen and oxygen atoms. MRI relies on the magnetic properties of hydrogen atoms to produce images. The hydrogen nucleus is composed of a single proton with no neutrons. As a spinning charged particle, this produces a magnetic field called a magnetic moment. Normally, the protons are orientated randomly, so there is no overall magnetic field. The components of the MRI system include the primary magnet, gradient magnets, radio frequency coils, and the computer system. MRI differs from imaging such as plain film radiography and CT scanning, as it uses magnetic fields and radio frequencies rather than ionizing radiation. The primary magnetic field refers to the strength of the static permanent field, for example at 1.5 or 3T. Hydrogen atoms align parallel or anti-parallel to the primary field B0. This is called longitudinal magnetization in the long axis of the magnetic field. A greater proportion of the hydrogen protons align in the direction parallel to the primary magnetic field or low energy state than align anti-parallel to the primary magnetic field, the high energy state. The net result, called the net magnetic vector, is therefore in the direction of the primary magnetic field. This is orientated in the patient's long or z-axis. The protons spin on their axes much like a spinning top. This is called precession. The precession rate is called the Larmor frequency. When protons precess together, this is known as in phase. When protons precess separately, this is known as out of phase. The frequency changes in proportion to the magnetic field. At 1.5 Tesla, this is 63.9 megahertz. The gradient coils generate secondary magnetic fields over the primary field. They are located within the bore of the primary magnet. They are arranged in opposition to each other to produce positive and negative poles. The arrangement of these gradient coils gives MRI the capacity to image directionally along the Z, X and Y axis. There are 3 gradient coils which are named according to the axis along which they act. Gradient magnets alter the strength of the primary magnetic field, thereby changing the precession frequencies between slices. This can then be used for slice selection and localization in the X, Y and Z axes, called spatial encoding, of MR images. The Z gradient runs along the long axis to produce axial images. The Y gradient runs along the vertical axis to produce coronal images, and the X gradient runs along the horizontal axis to produce sagittal images. The radio frequency or RF coils are used for transmitting the radio frequency or RF pulse and receiving signals in MRI. They come in many designs altered to best suit each body part, all aiming to improve signal-to-noise ratios to produce the best possible diagnostic images. The RF coil is used to transmit a second magnetic field or RF pulse, which results in a disturbance of the proton alignment. Some low-energy parallel protons flip to a high-energy state, decreasing longitudinal magnetization. Secondly, protons become synchronized and precess in phase. As a result, the net magnetization vector turns towards the transverse plane, that is, at right angles to the primary magnetic field. This is known as transverse magnetization. The radio frequency or RF coil is used to receive signals to create images, as protons resume their normal state in the primary magnetic field prior to transmission of the RF pulse. This is called relaxation. Relaxation in the longitudinal axis is T1 relaxation. Relaxation in the transverse axis is T2 relaxation. After the RF pulse, several protons flip back to their low energy state, parallel to the magnetic field Z-axis, giving up their energy to the surroundings, the lattice. This results in changes to the longitudinal relaxation, known as T1 relaxation or spin lattice relaxation. On a plot of magnetization over time, magnetization increases with time. This is the T1 curve. The T1 relaxation time will vary depending on tissue composition and structure. For example, water molecules move rapidly and do not move into the lower energy state quickly, so T1 relaxation takes longer. After the RF pulse, protons that were in phase begin to dephase in the transverse XY axis. This is known as spin-spin relaxation. This results in a reduction in transverse magnetization. Plotting transverse magnetization in the XY plane versus time, transverse magnetization decreases over time. In reality, the spins dephase much quicker than T2 because of inhomogeneity in the magnetic field B0. The combination of T2 relaxation and field inhomogeneity is termed T2 star. T2 relaxation times vary between tissues. For example, water molecules move quickly, and as a result, there is less field inhomogeneity. Therefore, T2 relaxation takes longer. The net magnetic vector is the sum of longitudinal and transverse magnetization. The net magnetic vector spirals around the z-axis with net precession. The changing magnetic moment of the net magnetic vector results in free induction decay. This induces an electrical signal. The signal received by the RF coil is in the transverse plane and reduces as the net magnetic vector moves to the long or z-axis. The computer system receives the RF signal and performs an analog to digital conversion. The digital signal representing the imaged body part is stored in the temporary image space, or K-space. The K-space stores digitized MR signals during data acquisition. The digital signal is then sent to an image processor where a mathematical formula called Fourier transformation is applied, and the image of the MRI scan is displayed on a monitor.
Well, let us continue our discussion. I'd like to tell you a few words about this technique, a few more words. It is that I told more advanced technique allows us to get more information than just concentration of hydrogen, and this video have demonstrated what is this what is this more advanced technique. It is based on the not permanent but a pulse electromagnetic radiation. So this pulse makes the change in magnetization of protons, and after that the received signal is it can absorb information about relaxation of initial magnetization. So the pulse makes the proton to oscillate in phase, to precede in phase, so precess in phase, and then the precession relaxates and the protons become orientated mostly parallel to the axis of magnetic field, and the relaxation time depends on type of tissue. That's why we can create a picture of different type of tissues in our body using this technique. Well, I think you can watch this video again. If you are interested in this technique, you can find more videos, maybe at the same channel. You can find the channel of the authors of that video, and find there more videos which can be helpful to you. Now let us go to the next topic. We spend a lot of time for magnetic field. Now our next topic is electromagnetic waves. So the electromagnetic wave is a type of electromagnetic field in which the oscillating electric field creates magnetic fields, and oscillating magnetic field creates electric fields. So we have a wave which can which can travel far away from its source, and it can exist already independently of its source. For example, if we consider the force of interaction between 2-point electric charges, then electric field was just a useful tool for solving problem of finding force of interaction, because we can say that there is interaction and there are no any field. In case of static electric field, there is no way to see electric field independent of its sources. The same is true for static magnetic field. If we deal with static fields only, then the concept of field is not a new type of material. So the field is not a new type of material. It is just a useful tool for solving problems. But if we find a wave, then we can say that electromagnetic field is a new type of material, because the wave can exist without its source. The source can be, for example, oscillating charge. This charge can disappear. It can be associated with opposite charge. There are no manifestation of this charge anymore, but the wave produced by this charge exists, and the wave can exist for a very long time. You probably know that there is a space radiation which is called relic radiation, which was produced in very early universe, when universe was very hot, and it emits light from every point, every portion of um, matter was a source of some type of light, and that light, which was emitted about 14 billion years ago, it's still present and still travels through universe, and we can detect it. We can get this. We can obtain this signal from free space, and this signal is called relic radiation. It is not as bright as it was initially. Now it is in far infrared radiation or microwave radiation. So which means it's lost most of its energy, but anyway, its presence, it exists, and it means that we should consider electromagnetic field as a new type of material. Well, what can we say about the properties of electromagnetic wave? They can be characterized by three vectors: vector of electric field, vector of magnetic field, and a vector which defines the direction of propagation. So this vector, which is called a wave vector, is inversely proportional to wavelength of the electromagnetic wave. The wavelength can be defined as a distance between two similar points of wave. For example, if we discuss a harmonic wave, it can be the distance between two maxima of one of the field vectors. And what is important, that electromagnetic field is always transverse wave, so it is not longitudinal. The electric and magnetic field are perpendicular to the k vector, to the key vector, the k vector, the vector which describes the direction of propagation. So they are perpendicular to k, and they are perpendicular to each other. So this is a property of electromagnetic field. One more property is that they are oscillating in phase. where we have a maximum of electric field, we have at the same time we have maximum of magnetic field. So this is interesting property of electromagnetic waves. And since it is a transverse wave, it is perpendicular to the vector k, we can consider polarization. It means the orientation of electric field vector or magnetic field vector in a wave. And there are two basic types of elementary polarization, which is plane polarization or linear polarization. The wave of this type is represented on this figure. Or another type of polarization is circular polarization. In this case, the end of the vector of electric field, for example, is drawn a spiral in space, and this spiral moves with the speed of wave. And you probably know that the electromagnetic wave are traveling in space with the speed of light. So light is a type of electromagnetic wave. And according to modern theory, we can associate a portion of energy with some electromagnetic field. So this portion is called quant and quantum radiation, and its energy is proportional to the frequency of radiation. The coefficient of proportionality is known as Planck's constant. Planck is a scientist who have introduced this relation, this constant in explaining the radiation of hot objects, so the so-called equilibrium thermal radiation. It was a problem of classical physics, and it was solved by Planck, who introduced small portions of radiation called quants. And what is important for us that quant's energy is proportional to frequency or inversely proportional to wavelength. So the higher frequency, the higher energy of a portion, and that means the radiation with very high frequency can bear a portion of energy which is enough for ionizing atom. And if this takes place, if the energy is enough for an ionization, then the radiation is called ionizing radiation. And here is the so-called electromagnetic spectrum, which is the range of frequencies of possible electromagnetic waves. We can consider it in terms of frequency or in terms of wavelengths. In terms of wavelengths, it is, I think, more useful for understanding. So the larger wavelengths, the smaller frequency and the smaller energy. The lowest energies can be found in radio waves, which can have a wavelength as large as universe is. So the largest electromagnetic wave, which can wavelengths, which can be considered is the wavelength with the length equal to the infinite wavelengths, and of course its energy will be infinitely low. So we can not find we cannot detect this type of waves. In our everyday life, we deal with radio waves, which can have wavelengths from a few kilometers to a few centimeters. All this all this range is called radio waves. And after these radio waves in between 1 centimeter and 1 millimeter, there is a so-called terahertz radiation. It is usually distinguished between radio waves and infrared because this range, which is not shown on this picture, this range, which is called terahertz, is important because it is not so well studied as radio waves or infrared, because there are no good sources of radiation in this range. That's why, for the moment, this type of radiation is intensively studied. In physics of solid state, there are a lot of attempts to obtain the good emitter which works in terahertz range with the wavelengths of a few millimeters. And this can be helpful from the medical application point of view, because it is another type of transmission radiation which is not ionizing, which can allow to create new diagnostic tools. After the terahertz range, we have an infrared range, and infrared range and so-called ultraviolet range of radiation are they are surrounding the range of visible light. On this diagram, it is very narrow, but if we look at the range from another scale, you can see that it lasts from 700 nanometers and about 750 nanometers to about 380 nanometers. So the range, the wavelengths in this range change for 2 times. This is quite a wide range from the point of view of detectors. So our eye is able to see the light which wavelength changes 2 times. It is very wide from this point of view. And of course, visible light was known by people from very, very old time. Men always use light for seeing objects, for obtaining the most of information. And that's why visible light was the base of this spectrum scale. And when new type of radiation was found, was revealed, as they called infrared and ultraviolet. Infrared means more larger wavelengths than red, which is infrared, and ultraviolet means shorter wavelengths than violet. In the 19th century, that was all the electromagnetic spectrum consists of 3 parts: visible light, infrared, and ultraviolet. So everything what was smaller than visible light in terms of energy was called infrared. Everything which has for high energy was called ultraviolet. And later it was found when the radio waves were invented, when the devices to produce and detect radio waves were invented. The new spectral range becomes called radio waves. The same is true for X-rays. When they were found, they become a new spectral range, and after that, gamma rays appears. Well, you can take a look of some history of electromagnetic radiation or related physics. So the study of electromagnetic field starts from Maxwell's equation, and then Maxwell's equations are 4 equations describing electric and magnetic fields, and after those equations were found, it was understood that these 2 types of fields should be considered together, that we have one type of matter, one sort of matter, which is called electromagnetic field. And then from these equations, the basic consequence was the existence of electromagnetic wave. People didn't know that electric and magnetic fields can exist in a form of wave before Maxwell has written his equations. And when it was understood that those waves can exist, the physicist Henry Hertz built an apparatus to generate and detect them. And later, this type of waves was called radio waves. So here you can see the theory, the history of X-ray and gamma rays. And next topic we could discuss is optics, which is laws of geometrical optics, which is lenses and other related things. But I think we have no more time for this, so we will discuss it next lecture in 2 weeks. And now I'd like to tell you a few words about your tests. So first of all, well, let me stop this demonstration. Actually, there is no difference. So first of all, you have already one test in our university site system. I think I can stop the recording.